Hi everyone, I'm Yongqin, a fourth-year PhD student from USC. Today I will talk about my paper, LAORAM. LAORAM is efficient ORAM for large embedding table training. It achieves around 5x speedup over normal PathORAM. Embedding tables are widely used in both recommendation models and NLP models to make categorical data more meaningful for ML models to learn. On the right, we have a general structure of a recommendation model. Categorical data like gender, race are fed to the embedding tables, and the embedding tables will convert them into the embedding space. When embedding tables is processing the categorical data, a unique input to the embedding table will result in a unique memory access pattern, and the leakage of such access pattern can compromise input confidentiality. ORAMs like PathORAM are proposed to mitigate such leakage through memory access patterns. In short, PathORAM organizes data in binary tree format. The capacity of such binary tree is usually 4 to 8 times larger than your database size. Your data are distributed randomly on the path of the binary tree. In PathORAM, to access a data block, you need to read and write the entire path associated block. Also, you need to change the path of the access data block after every access. By applying PathORAM to embedding table, the leakage we mentioned earlier will be mitigated. However, PathORAM has a large overhead. It has lots of data movements and lots of metadata management. To reduce those overheads, we introduced LAORAM. First, we introduced the aggressive superblock formation based on the future. Second, we propose a novel tree structure called fat tree. Let's first look at the look-ahead feature. During the embedding table training, the training batches are known ahead of time. Thus, we could look in the future training batches and form large superblock sizes of 4 and even 8. To form a superblock, we will force data block in the same superblock to be assigned to the same path. Let's look at this example. If we know that data block A and data block X will be accessed together in the future, instead of assigning data block X with a random path, we will assign the data block X the same path as the block A, such that in the future, on the next axis, instead of accessing 2 random paths from the tree, we can just access 1 single path to read both blocks. Besides the aggressive superblock formation scheme, we also introduced a novel binary tree called fat tree, where the near root nodes are given more memory spaces. When we're using a large superblock, managing a metadata structure stash in the PathORAM become time-consuming, and we use this fat tree structure to mitigate the pressure on the stash. With our aggressive superblock formation and our new tree structure, we can reduce the PathORAM overhead on embedding table training by around 5x. Thank you for your attention, and I encourage you to attend our in-person talk and read our paper for more details.